In the previous video, we calculated the second moment of area for a beam based on given allowable deflection information. We had a beam that was subjected to various different loads, and we specified that that beam should only deflect by a maximum of 3 mm at the centre of the beam. Now, once we'd calculated our allowable second moment of area for that condition to be satisfied, we used the universal I-section beams tables shown on the screen in order to select a suitable I-section beam. Now, if you recall, the beam that we selected was the beam with designation 152 by 89 by 16, second from bottom there. And what we did is we took the second moment of area for that beam about the x-axis of 834, and we calculated the actual deflection at the centre of that beam. Now, what we're going to do in this video is we're going to use finite element analysis in order to confirm and validate those results. So the first step of that is to produce the geometry of the beam. And if you recall, our beam was 5 meters long, and we're going to produce the I-section beam as shown at the top of the page there. So the first thing we need to do is take a note of some of these key dimensions. We have the overall depth or height of the beam labelled as h, and from the appropriate column in the table, we can see that that value is 152.4 millimeters. The next dimension that we're going to take there is the dimension b, which is the overall width of the beam, and referring to the table, we can see the overall width of our chosen beam is 88.7 millimeters. We have the thickness of the flange labelled as T on the diagram, and referring to our table, we can see that the thickness of the flange in this case is 7.7 millimeters. We also have the thickness of the web labelled as S, and referring to our table of values, we can see that that's 4.5 millimeters. The final measurement that I'm going to take here is the radius of the fillet R, and we can see the radius of the fillet for all of these beams is 7.6 millimeters. So now I've made a note of each of those measurements, I'm going to go to Fusion 360 and I'm going to create the geometry of the beam. Okay, so the first step in creating this geometry is to create the sketch of the end of the beam. So if I start a new sketch and select the plane on which I want to draw, I can then begin creating my sketch of the beam. So I'm actually going to draw half of the section and then I'm going to mirror it. So if I take the line tool and begin to create the general sketch, and then I can begin to add some dimensions to this. So the first dimension here will need to be half of the overall width of the beam. Now the overall width of the beam was 88.7 millimeters, so I'm going to type 88.7 divided by 2. The thickness of the flange was 7.7 millimeters, which is this dimension here. If I continue with my sketch, once again this distance here is going to represent the thickness of the flange, 7.7. And then I can close off my sketch. So let's add a few more dimensions to this to fully constrain our geometry. We have the overall height of 152.4. And the thickness of the web was 4.5 millimeters. Note that here we only have half the thickness, so the distance from here to here is going to be 4.5 over 2. Now we can mirror what we have here to produce the other half of the section. So we click on Mirror, select the objects, select the mirror line, and click OK, and finish our sketch. So now we have the section of our beam. The next task then is to extrude this, and we want to extrude this to produce the full length of the beam. We specified previously that the beam was 5 meters long, but I'm actually going to make this slightly longer, and you'll see the reason behind this in a moment. So instead of 5,000 millimeters, I'm going to make this 5,100. So I'm making the beam 100 mil longer than necessary. I'm creating a new body and clicking OK. So now I have the general geometry of my I-section beam. The last thing to add are our fillet radiuses of 7.6 millimeters to the inside edges. So if we select our fillet tool and we have this edge, we have the underside edge, and then turning our beam round, we have the same two edges on the opposite side. So we have our inside edge here and our inside edge on the opposite side. Note that we have 4 edges in total. The radius, 7.6 millimeters, and click OK. We can check that this has been applied correctly by zooming in on the end of our beam. And what we should see is that we have our radiuses applied at each of these internal edges, and we can see that that's now correct. So now we have our general beam geometry. The next thing we need to do is create 2 supports for this beam to sit on, and we're going to create some prisms because what we want is our beam to sit on a sharp point. So I'm going to create one of these, and then once I've created one of these prisms, I'm going to copy it to the second location. So for this prism, what we need to do is ensure we're drawing on the correct edge of the beam. So I'm going to create a sketch, and I want to ensure that I'm drawing on this front face of the beam. Now, if you recall, we actually drew this beam 100 mil longer than necessary, and that was done so that we could create our prism 50 mil from each end. The reason we do that is to ensure if this beam deflects, that the beam isn't going to fall off of the supports. So what we need to do is do a construction line 50 millimeters long. And from there we can sketch our prism. Like so. I'm going to switch to the front face to check the dimensions on this. And I'm going to make my prism out of an equilateral triangle of sides 100 millimeters. So the way I'm going to do that is specify one of these lengths as 100 mil. And then I can specify each of my angles as 60 degrees. And there we have an equilateral triangle 100 mil by 100 mil by 100 mil. Now that we have our sketch, we can extrude this, and we need to extrude it through at least the width of our beam. So if we select extrude and select our direction, we can see at the moment that that's in the negative direction. And our beam had an overall width of 88.7 millimeters. Now I'm going to set this at 88.7 just for consistency. Like so. So now we have our prism as a separate new object or a new body, and we have our beam sitting on the prism. So now we have one prism, we need to create a duplicate. I'm going to use the move copy command. I'm going to select my prism. I'm going to check create a copy. And I'm going to begin moving in the required direction. Now we need this to be exactly 5 meters or 5,000 millimeters. And then we can click OK, like so. Now what we have is we have a prism 50 millimeters from this end and a prism 50 millimeters from the other end. Now the other thing that I'm going to do before we go to the simulation workspace is I'm going to specify the material properties for this beam. If you recall, the elastic modulus for our beam was 190 gigapascals, And what we don't know at the moment is what the elastic modulus is for the steel that's being used here. So if I go to Modify, Physical Material, and then double click on the material that's being used in this design, by going to Advanced, I can inspect the physical properties. Physical properties, mechanical, because it's the elastic modulus we're concerned with, and what we can see is the elastic modulus, or the Young's modulus of the material being used, is 210. Well, we need to change that to 190. Now when we click Apply and OK, a new material is created. And the reason a new material is created is because we're trying to overwrite the properties of the existing material. Here we have our new material, and we can double check the properties of that once again by double clicking, going to Advanced, and we can see that our new material has an elastic modulus of 190 gigapascals. I've left all of the other properties the same for the time being because it's only the elastic modulus that we're concerned with here. What we need to remember to do is drag that property or drag that material onto our beam and release, so that now our beam has the associated properties with our modified steel. Okay, so now everything is complete in the design workspace. We can switch to the simulation workspace. We're going to do a static stress simulation. And now we can set up our new study. The first thing I'm going to do is just check that the material properties have been applied. So if we go to Study Materials and click on the Properties tab, then each of these components has been assigned properties. What we see here is the Young's modulus for our simulation material is 190 gigapascals. So those properties have carried through from the design workspace. Now that I'm happy with the material, I'm going to go to the constraints. And I'm going to assign a number of constraints to this model. First of all, I want to fix my two prisms in space. So I'm going to use a fixed constraint, and I'm going to apply that to the bottom of each of our prisms. So if we go to our first prism, and we need to apply on the bottom surface a fixed constraint. So here on the bottom of the prism, we have a fixed constraint. Now before I OK that, what I also need to do is apply exactly the same condition to the bottom of the other prism. Each of these prisms are fixed in space. So once again, I'm going to click on the bottom surface. We have two surfaces selected, and we're applying a fixed constraint. OK. Next, I'm going to apply a second constraint, and this constraint I'm going to apply to the inside face of our beam. We could apply this to a number of different faces, but the reason we're going to apply a frictionless constraint here is because we don't want any lateral deflection of the beam. So we only want this beam bending in one plane, or about the y-axis in this case. We don't want it deflecting sideways as a result of the lobes that are being applied. So I'm going to specify this using a frictionless constraint and click OK. So now each of my supports are fully constrained, and my beam is constrained so that it can only deflect in one direction. Next, I'm going to apply my lobes. Now, as you recall, we had two loads being applied. We had a load of 1050 newtons, and that was a point load. So I'm going to apply the point load first of all. Now, the way that I do that is by selecting the face that the load's going to apply on. But you see, by default, it wants to apply that as a uniform distributed load. Well, I don't want a uniform distributed load, so instead I'm going to click on the Vectors tab here. And if we refer to our diagram in the top right-hand corner, we can see that we want the load to be applied in the Z direction. We have a load of 1050 newtons. Now, once again, referring to the diagram, we can see that that arrow is pointing upwards. That's not pointing in the correct direction. So what I'm going to do is specify minus. Minus 1050, we have a point load acting downwards at the centre of the beam. OK. Now our second load was a uniform distributed load of 110 newtons per metre. And in our example, our beam was 5 meters long. However, please recall that in this case, we've actually made the beam slightly longer in order to allow for our beam to sit on the two prisms. So here, the length is 5.1 meters. Now the way that I'm going to do this is I'm going to specify the top surface once again. This time we want a uniform distributed load, the magnitude of which is 110 times 5.1, which actually comes out as 561 newtons. We could allow Fusion to do that calculation for us, or we can input it manually. So now we've set our constraints, we've applied our loads. The next thing we need to do is to set our contacts. Now we're going to use manual contacts here. And the contact type that we're going to use is called separation. Now the reason we're using a separation contact type is because we want to tell Fusion that our beam is allowed to move independently of our prisms. So we need a separation contact between the underside of our beam and the edge of our prism. So if we select contacts and we go to manual contacts, Fusion's going to ask us if we first want to generate automatic contacts. In this case, I'm going to click no. My primary body then is my beam, and my secondary body is my prism. The selection set for the beam is the underside of the beam, and the selection set for the prism is the top edge of the prism. We're going for a separation. My coefficient of static friction I'm going to set as 0 because I don't want any friction between them two surfaces. And I'm going to check automatic max activation distance for simplicity. I'm going to click OK to apply that set, but remember to do both ends of the beam. So at the opposite end of the beam, we're going to be specifying exactly the same contact. We're going to do a manual contact. We're going to select the beam as our primary and the prism as our secondary. We're going to select the underside of the beam as our selection set, and we're going to select the edge of the prism as our second selection set. The same conditions are going to apply: separation, 0 friction, automatic max activation distance. OK. So now we can carry out our pre-checks, and the pre-checks highlight a warning. It tells us that some of our components might not be fully constrained. If we take a look at our degrees of freedom view, let's switch our colour for fully constrained, we can see that our two prisms are fully constrained and our beam is only partially fixed. Well, we only want our beam to be partially fixed because what we have here is a simply supported beam. The beam is free to move and we want it to be able to slide on those prisms in order to allow the maximum full deflection. So I'm going to close that and I'm going to ignore those warnings for the time being. The next step then is to apply our mesh. So if we click Solve, Generate Mesh, and Fusion is going to assign a mesh to that geometry. So since we already have a relatively complex geometry, I'm just going to work with the mesh that's been assigned. We can see that the mesh is relatively dense, and we want to keep our computation time to a minimum since we're just looking to validate the results that we'd already obtained. So next then, I'm going to solve. We have a warning here due to the constraints, but we're going to run the simulation. Okay, so now our simulation is complete. If we close the job status window, and we'll close the result details for the time being, what we can see is that as expected, our beam is deflecting. The outline here shows the original position, and here we can see an exaggerated new position. But what we're going to switch to here is we're going to switch to displacement. And what we can see is we have a maximum displacement of 1.641 millimeters. Now, when we did the hand calculations, this came out to be 2.29 millimeters. So we can see that our results here are of the correct order of magnitude. Now, as expected, the maximum deflection there is at the centre of the beam. So we have a maximum deflection of 1.6 millimeters instead of 2.3 millimeters. Now, what are some of the reasons that can account for these differences? Well, first of all, our beam is slightly oversized, and although this won't make a great deal of impact, the overhang either side of the prism, as we see at the end of the beam here, would actually cause an opposing bending moment. So that may account for a small difference. As we know with numeric simulations, there are potential errors due to the density of the meshes used and so on, where a more refined mesh gives a more accurate result. One other thing to consider here is how we've specified our supports. We have both of our supports as fixed supports, whereas normally when we look at simply supported beams, we have one support fixed and the other one free to move or free to roll. The challenge with specifying that on this type of model is that the support would actually slide away from the beam and cause the beam to fall off of the support. So we've had to make some adjustments and allowances for that. Potentially the largest factor here affecting our results would be our mesh density, as here we've just used the mesh density that was assigned automatically. The important takeaway, however, is that the results that we've generated are of the same order of magnitude as our hand calculations, where our deflection here is 1.6 millimeters, and the maximum deflection using our hand calculations was 2.3 millimeters. Anyway, I hope you found this video useful, and thanks for listening.